Let's look at this photograph of an early locomotive engine. The entire premise of machines like this is taking thermal energy, heat from burning coal, and turning it into physical movement to drive the wheels. To understand the precise physics behind that conversion, we need to strip away the complex machinery. Imagine a simple metallic cylinder filled with a gas, capped by a movable piston. We place this metallic cylinder into a massive thermal reservoir. This is a surrounding environment, like a giant water bath, so large that its overall temperature never changes, no matter how much heat it gives off or absorbs. As the gas inside our cylinder expands, it pushes the piston upward. In physics, applying a force over a distance like this means the gas is performing mechanical work against the outside environment. But if you attach a digital thermometer to the side of the cylinder during this expansion, you'll see a strict physical anomaly. The temperature reading remains completely frozen. If the gas is expending its own internal energy to push that heavy piston, the math suggests it should be cooling down, yet the temperature doesn't drop by a degree. This specific scenario is known as an isothermal process. In thermodynamics, an isothermal process is a change of a system where the temperature remains entirely strictly fixed throughout the event. This constant temperature is maintained by the metallic walls of our cylinder. They are perfectly conducting, meaning they allow heat to flow freely from the massive surrounding reservoir directly into the expanding gas inside. For this to actually work, the expansion has to happen at a very specific speed. It must be quasi-static, meaning the piston moves infinitely slowly, giving the gas constant time to absorb heat and equalize its temperature with the outside bath. Because the expansion is infinitely slow, the heat seeping in perfectly offsets the energy spent pushing the piston. That continuous heat exchange is the only way a gas can expand and do physical work without experiencing a drop in its own temperature. This chart plots the pressure of our gas on the vertical y-axis against its volume on the horizontal x-axis. To map its behavior, we use the ideal gas equation, P times V equals mu times R times T. Because our process is isothermal, the temperature T, number of moles mu, and gas constant R are all locked in place. Rearranging to solve for pressure gives P equals that constant divided by volume. This is Boyle's law. Tracing this relationship on our graph, starting from an initial compressed state and moving to a final expanded state, we get a smooth, downward-sloping curve. The specific curve is called an isotherm. Looking at this shaded area underneath the isotherm curve, we can measure the physical effort of the gas. The total mechanical work done by the gas equals the exact area under this curve. To calculate that area, we use an integral equation. Work equals the integral of pressure with respect to volume. We swap out the pressure variable for its equivalent, mu times R times T divided by V. Because mu, R, and T act as constants, they move completely outside the integral. The integral of 1 over volume is the natural logarithm, resolving the equation, work equals mu RT times the natural log of final volume divided by initial volume. If the final volume is larger than the initial volume, the natural logarithm evaluates to a positive number. This proves mathematically that as the gas expands, it absorbs heat to perform positive work on the surrounding environment. Returning to our physical cylinder, we look to the first law of thermodynamics. This equation is the ultimate ledger of energy conservation for any system. The ledger tracks exactly 3 variables: delta Q, which is the total heat supplied to the system, delta U, the change in the gas's internal energy, and delta W, the physical work done by the system. A foundational rule of ideal gases is that their internal energy, U, is dictated by exactly one metric, their temperature. Internal energy is simply the sum of the kinetic energies of the molecules in motion inside the container. Now remember the digital thermometer attached to our cylinder. Because this is an isothermal process, the change in temperature is exactly 0 from start to finish. Because the temperature is strictly locked, the kinetic energy of the molecules cannot increase or decrease. Therefore, any change in internal energy, that delta U variable, is physically impossible, locking its value at 0. Looking at this equation, if delta U is exactly 0, we can strike it from our first law ledger entirely. Removing that variable reveals the simplified ultimate equation for an isothermal process. Delta Q equals delta W. Mapping this mathematical rule directly back to physical reality, every single joule of heat, delta Q, that the gas pulls in from the infinite thermal reservoir is converted perfectly and entirely into the mechanical work, delta W, required to physically lift the piston. The gas doesn't cool down because it acts as a perfect frictionless conduit. It transfers thermal energy directly from the external bath into physical action, without keeping a single drop of energy for itself.